All right. In this example, we're going to do example 6, example 7, and example 8 all together. We'll just kind of space them out and link them in the notes. All right. So in the first one, we have cosine of theta times 12 is equal to our radius. And we want to find the area of this circle. Okay. So we have area is equal to the integral. And we saw from the notes previously, this was R1, no, I think it was not R1. What do we call it? Alpha and beta, and then this is 1/2 R2 squared minus R1 squared d theta. This is going to be 0 for us. This, if you remember from the first example, this is going to go from 0 to pi and not 2 pi for the complete circle for the graph. That's what we saw in that first example in the graphing it by hand. And so this simplifies the formula quite a bit, that this is going to be then the integral from 0 to pi 1/2 of R12 cosine theta squared d theta. Okay. So 12 squared is 144. Half of that is going to give us 72, the integral from 0 to pi. And then cosine squared, wait, theta, d theta. If I integrate this, I'm going to use the power reduction. So 1 plus cosine of 2 theta divided by 2. So that's going to reduce this in half again. And so you'd have the integral of d theta from 0 to pi of 72. 72 divided by 2. I should have done that. What is that? 3 gives you a difference of 1. 2, that'll be 6. So this is going to be 36. And then this is going to be the integral of 1, or d theta, from 0 to pi, plus another 1/2 coming out from the 2 here. The integral of cosine is a negative, is a positive sign, 2 theta evaluated from 0 to 2 to pi. Okay. And this is going to give us just theta evaluated from the same limits. So if we look at this, this is going to give us pi minus 0. That would be the upper limit minus the lower limit here. And then plus 1/2. Well, sine of 2 pi is going to give us 0. Minus the sine of 0 is 0. So that's just going to give us 0. So there's 0 contribution from this last term. And so the very final result then is that we get this is equal to 36 pi is the area of this circle. Okay. All right. So we'll jump to the next one. And for example 7, we want to find the area of this lemon. And so we're going to have 1/2 the integral from 0 to 2 pi of, well, this is the thing, 4 plus 2 cosine theta squared d theta. Now, we can integrate this by foiling this out, and then it'll be pretty straightforward. Foiling it out, you'd have 3 terms, and then on the last term, you'd have the cosine squared term, so you'd have to do the cosine reduction, so you'll get 2 more terms coming out of that. I went ahead and threw this into GeoGebra, and I got that this exact form as it was put in gave me 18 pi. Let's go ahead and verify that and show you how to input that in case that's not clear. But that is the result from example 7 for finding the area of that shape. So let's go ahead and input this in then, and we'll have that the area is 1/2 times the integral. We're going to have double parentheses here, 4 plus 2 times cosine of theta. And then on the outside of that, we're going to square that. That's the r squared part. And then let's get the limits of integration. So theta is going to go from 0 to 2 pi. And as you get the result of 18 pi is the resulting area for the limicon in example 7. All right, I hope that was helpful, and we're going to jump into example 8. All right, this is example 8, and in example 8, we have 4 plus 8 times cosine of theta is our graph. And so if we zoom out over here, let's get a good look at what does this look like. So there is our wonderful little shape, or little limicon. And so we want to find the area of this little guy here. And so we got to figure out, okay, so where does this value of theta first, start here, and then when it traverses around and comes back around, where does it end up back here? Okay. So those are the two values that we need to find. And so to do that, we're going to jump over to solving that. And then after we do that, we'll calculate the integral. Okay. So we have r equals 4 plus 8 cosine theta. And so when we were looking at the graph, right, we had this little loop, and it kind of did, well, not super accurate. You can't really see it with the reflection of the light. Sorry about that. So what we're looking for is what are the angles that correspond to this and to that. That allows us then to integrate along this point to find the area, and it's that little inner shape there. So in order to calculate that, then we're gonna notice that the radius actually happens to be 0 at that point, right? We're back at the origin. So 0 is going to equal 4 plus 8 cosine theta. So if I subtract 4 from both sides and then divide by 8, I get negative 4 over 8, which is negative 1/2, which equals cosine theta. Now, when is cosine of theta equal to negative 1/2? Well, if we think about the angles, right, where is cosine? Cosine's your x-coordinate. Where's cosine negative? Cosine's negative in the second quadrant and in the third quadrant, which is perfect because those are the two angles that we need. Now, we need to figure out, okay, so what angle would give us that? And so if you think about in the first quadrant as our reference, there are two values, pi over 6 and pi over 3, where you get 1/2. Now, the x-coordinate is the first coordinate, and if it's 1/2, it means it would be the shortest side. And so that means it's got to be this one, which would be the higher of the two, which is pi over 3. Okay, so that's going to be our reference angle then. And so this one here would be, this is pi. And so we come up that same amount, that's going to be minus pi over 3. And then likewise, if this is pi, we're going to go pi plus pi over 3 to get to that little extra bit there. Okay, if that's not clear, I understand that might be a little confusing. So let me erase this and consider a straight line. This entire angle is pi. And what I'm saying is that we're going to come back just a little bit more. And how much more are we coming back? We're coming back that reference angle, that pi over 3. So the reason why we're subtracting pi over 3 for this upper angle is because the entire line is pi, and we're scooting back pi over 3 amount because we're after the measurement of this angle here. Remember, the theta is always measured from the positive x-axis by convention. Okay, and likewise, for the line that's down here, this whole length here is pi, and I need to go a little bit more to get down to this, to get down here. And how much more do I need to go down? I need to go down pi over 3. So I'm going to add. So I'm going to go starting from here. I'm going to go to pi, and then a little bit more down to pi over 3. And so those are the reasons you're subtracting or adding that reference angle, which you can find from the quadrant 1 values. Okay, so what does that mean? That means that theta is going to be equal to pi minus pi over 3. This will be our first angle, and then our second angle will be pi plus pi over 3. This was what we called beta, and this is what we call alpha. Okay, so those are angles of integration. And so with these, then we can utilize technology and the formula that we just saw in GeoGebra to integrate that result. In other words, what we're going to be integrating here now that we have the angles is the area is going to be equal to 1/2 the integral from alpha and beta, these two values that we just found, and then our theta, so 4 plus 8 cosine of theta squared d theta. Now we could multiply this out and then also carry out that, but let's use technology to simplify that result. So let's go ahead and jump over to GeoGebra and do that now. Okay, so there's our function. So we're going to go ahead and see if we can get that interval up, and 4 plus, so we're pretty close with this one. This is going to be 4, and no, sorry, it's going to be an 8 and a 4. So those are the same. And now I just need to change my limit of integration here. So we saw that that was pi minus pi over 3, and that was pi plus pi over 3. And so if we throw those in, we get that this is equal to, looks like 16 minus 24 square roots of 3. So that's the exact value. Let's see if we can make it numeric and maybe get a numerical value for that. So it says it's about 8.7. So that's exactly what we should expect. All right. All right. That was example 8 and of these 3 examples. So I hope that was helpful, and I'll see you in the next video.